going to get started. Thanks everybody for staying at the session. Can everybody hear me well? All right. Like I said, thanks everybody for coming, and thanks to John and Julio for their previous presentations. So today I'm going to follow up on their discussions with a discussion about optimal experimental design and statistical power. This is going to be based on Chapter 4 of John's new book. And before getting started, I'd just like to say that statistical power should be in your minds basically from the beginning of any project. So whether you're starting with a research idea and deciding how to test the theory, or you're talking with a research partner and brainstorming about designing a field experiment or impact evaluation, the first things that should run in your mind are things like, how many treatments do I need to test the theory? What's the unit of observation? How many workers or households will be in the sample? And then how much money do I have available, or how much do I need to raise? And so today we're going to talk about sort of overarching framework for thinking about these questions, and a number of design characteristics and statistical power issues to consider when designing your experiment to give you guidance on how to do that. So a bit of a roadmap today. We're going to cover some of the basics of statistical power, which many people are probably familiar with, but we'll start there and go through what's called a pen and paper example, in which you can have in the back of your mind, which is very useful to quickly do the math when thinking about or speaking with a firm or NGO or other partner to come up with a quick, rough research design. Then we're going to talk about power with the most basic experimental design, which is a dichotomous treatment with a binomial outcome. Then we'll expand on that and move to multiple treatments with continuous outcomes. And then we'll talk about when the cost of treatments might be unequal. For example, when one or more treatments might be very costly, but your control or other treatments are not, and how we take into account that when we're designing, when we're coming up with the sample size and how to allocate units to treatment. And then we're going to talk about a little bit about cluster designs and imperfect compliance. So I'm not going to have time today to talk about everything. There's a number of other considerations to take into account that are in the textbook chapter, including simulation methods for sort of real world settings where these closed form solutions might not be helpful. Another issue that's very important is multiple hypothesis testing. Increasingly, editors are always asking you to control for multiple hypothesis testing. And if you're dealing with a panel data setting, and then how these might affect your power calculations, as well as ways to increase your statistical power. Okay, so a key feature that we learned from previous discussions is that the assignment mechanism is going to play a fundamental role in determining which data points are missing and which are observed. And so as you are the allocator of units to treatment and control, you're going to take on this role in the data generating process, and it's completely in your hands now. So once you have this in mind, what aspects of the theory you want to test, this sort of formal role of data generation begins. And you're going to have to consider the appropriate sample sizes, which basically boils down to taking into account two things. One is the optimal number of units, and then that you're going to randomize, and then how you arrange those in across treatments. So what we're going to do now is we're going to discuss some of the trade-offs that experimenters face given the limited sample sizes that we have in experiments due to a number of things, such as your budget or how many units you have available to you. So we'll cover this nuts and bolts discussion of carrying out this task in an optimal manner, and there's three key elements to statistical power that we're going to use to ground this discussion. So the first is the significance level of your test, right? So this is the probability of falsely rejecting null hypothesis, which we call type 1 error. We're trying to reduce type 1 error, and this is the sort of trying to reduce false positives. So generally, we use an alpha equal to 0.05, which gives us a significance level of 95%. So the second is the statistical power of your test. And this is type 2 error, or the probability of detecting an effect if there is an effect to be detected. And this is something we worry about a lot. So what we need is, if we do have a treatment effect, we need to be able to detect it. And so many times what happens in an underpowered experiment is maybe you have an effect. Let's say you find a treatment effect of 0.05. But it's insignificant, and you can't actually distinguish whether that's due to the treatment or that's just a spurious result. And so what we're trying to do is we're trying to maximize this power and our ability to be able to say, if we do find an effect, that it's statistically significant. And generally, the power that we use is about 0.8. Sometimes you can use 0.9 as well, but it's best not to go below 0.8. So when we're moving forward and thinking about our power calculations, these are the values we're going to have in mind for these. And then finally is your minimum detectable effect size. And I'll talk a little bit more about that later, but this is the magnitude of your treatment effect. And many times this is going to be driven by things like your partner's goals, your theory, etc. So I'll, in the following slides, I'll discuss more what we mean by minimal detectable effect size and sort of how that plays into the role of in power calculations. So generally, as economists, the usual approach we take with observational data is that we're running a standard regression model, and we're going to think about what's the probability of observing the coefficient we observe under a true null. So like I said before, with power calculations instead, we're going to take that significance level as given, and we're going to think instead about the probability that we're going to correctly reject the null hypothesis, or rather, how do we increase the probability that we're going to reject the null if we see some sort of treatment estimate. So to give you a visual illustration of this, so in this figure, the curve to the left shows the distribution of the treatment effect, what we call tau hat, under the null hypothesis of no effect. And the curve to the right shows the distribution of tau under the alternative hypothesis of effect size tau. So the sum of these green parts here for the on this null hypothesis bell curve, and that's going to represent the significance level alpha, which is generally 0.05. And this is the probability of this type 1 error, as I was saying. And then this green, or the red part here, is the probability of type 2 error, beta. So power is given by the probability that the statistical test will correctly lead to the rejection of the null hypothesis. So looking at this figure, we can already see a number of ways to increase power, how to think about power, and reduce this beta. So if we hold this effect size tau fixed, so the one main way that we do this is by reducing the variance in these curves. So if we shrink those curves and make the variance smaller, what that's going to do is that's going to decrease that beta, and it's going to give us more power to detect our effect. Similarly, if we hold the variance fixed, we can think about detecting larger or smaller effect sizes, because as that variance shrinks, we can get closer and closer to that zero and still have sufficient power. So this is going to be akin to moving that effect size left or right. So let's look at this in the context of an experimental design framework and how we're going to be estimating our treatment effect. So here we have our outcome yi. So these are the outcomes that we measure after the experiment has taken place under the different treatments. D1, let's call that treatment, and D0 equals control. And so we're modeling this yi as the sum of yi for the observations that are in control. And then in the second term, if di equals 1, we're going to be observing the yi for those that receive treatment. And so now we're going to think, what we're going to try to do here is we're going to estimate this tau I, this term next to the di, and then we're going to think about the precision of this average treatment effect. So that's what we're going to call our average treatment effect. And in this regression framework that we see in equation 2, what that's going to be is akin to regressing yi on our constant as well as the indicator for our treatment effect, and that's going to give our estimate of tau I. So here we have the variance of this estimated average treatment effect, which under our exogeneity assumptions is going to be equal to the variance of our outcomes over the variance of the sample size, or over the sample size, sorry, or that's similarly equal to the variance in the unobserved component of our outcome variable over the sample size times the variance in the treatment propensity. So this value, as you can see here, is going to be increasing in the variance of the unobserved component. It's going to be decreasing in the number of observations, and it's going to be decreasing also in the variance of the treatment propensity. So as if we recall from the figure I showed earlier, this is the value we would like to decrease, and this is going to increase our power. So right off the bat, this reveals two ways to increase power. One is to increase the sample size, right? So if we increase this n, that variance is going to decrease. but that also might be the most costly way that we can increase power. Or we can increase the variance in our treatment variable, which I'll return to later when we talk about treatments with different costs. So let's go through a quick example of how we can calculate power with two treatments and a continuous outcome. So in this context, we have n, which is essentially what we're trying to figure out and what we're going to solve for. And this total n is going to be made up of the number of units in our treatment and the number of units in our control. And that's going to be the choice of the researcher. And here we're going to denote these as n sub 0 and n sub 1. Then we're going to have the average of the outcome in the control group with its associated distribution, right? So this is just the sum of all the outcomes in the control group over the number of observations in the control group. Similarly, we're going to have the average of the outcome in the treatment group with its associated distribution. And that's going to be the sum of all those outcomes over the number in that group. And then our minimal detectable effect is just the difference in the means in the outcomes of the treatment and control for a given level of power and statistical significance, right? So this is very important. The MDE is conditional on the values that we use for significance and power. Or put another way, the MDE is the effect size below which we may not be able to distinguish that the effect is different from 0, even if it is. So with very large samples, we can actually detect quite small MDEs, but generally the idea is that we want a design that will minimize this MDE. So to make any judgments about power and what we'll need to calculate power, we're going to need to make some judgments about the variances in our outcomes and what the desired MDE will be to determine the sample size. So then the question is, where do these come from? And you can think about how we might come up with these values, right? So we're given the alpha and the beta, and we need to come up with values for sigma squared for the variances of our treatment and control, and then also the minimum detectable effect size. So we're going to have to gather potentially a bunch of data and try to think about how to calculate these. Luckily for us, as I said before, we generally use alpha equal to 0.05 with a significance of 0.95 to reduce the type 1 error. And our test should be powered at least 0.8, so that we already have. That's nice. So then how do we get these variances? So the variances can actually come from a number of places. They're ideally found in baseline data. So if you're working with a firm or with administrative data, this can be quite easy to calculate as you might have access to lots of data. If that's not available, you can calculate these using a number of other potential data sources. So if you have data that's from a similar population, say in a different area of a country, or potentially even a different country but might have a similar population, or you can go to other papers that are written on the topic. So you might have other studies that are similar to the study that you're doing. And these would also have potentially some values of these variances that you can use, preferably, again, among as similar populations as possible. And generally, it's typically assumed that the outcome variance is going to be the same across treatment arms, but that's not always the case. So many times, if you assume that they're going to be the same across treatment arms, you can just have a measure of the variance from your data like that. So the minimum detectable effect can be expressed in a couple of ways. One is to just say the effect size is the level. So let's say effect size is $50. Or you can express it as a percent. So let's say your mean is 1,000 and you have a $50 effect size, that would be 5% effect size. Or sometimes it's going to be expressed as a ratio relative to the standard deviation of the outcome variable. So in the example below, let's say the mean of your outcome is $1,000 with a small standard deviation of $166. And you're trying to think about the sample size for a large intervention, let's say to improve outcomes of rural farmers, so the incomes of rural farmers. So if we think about a 0.3 standard deviation effect size, which generally is considered a sufficiently large effect size, that would translate into about $50. Now, is that actually a large increase? Well, this is debatable, but in this case, if it's a very costly program, it might actually be cheaper to just give all the treatment households $50 than to try to detect a 0.3 SD effect size. So the actual MDE that you come up with should be this sort of minimum improvement in outcomes required for the partner to determine the program's benefits and if they're worth the cost, or to scale the program, or from your theory. So it's a sort of process through which you come up with this effect size. And sometimes published studies evaluating similar interventions, similar to the variances, will typically provide an optimistic estimate of reasonable effect sizes. But sometimes, you need to make sure when you're looking through those things like compliance, right? And those are really going to affect what effect size you're able to estimate. And so in the past, some people have used rules of thumb, such as 0.2 SD would be a small effect size, 0.5 SD would be a medium effect size, 0.8 SD would be a large effect size. But as we saw in the previous example, these might not be sufficient in your context. So let's move forward to the mechanics of how to calculate your optimal sample size. So you're going to need to specify your null hypothesis. Generally, that's of no effect, and then your alternative hypothesis. And that's going to take a specific value. And then the goal is to find the sample size needed that you do not reject the null when it is true, the true outcome, more often than alpha. So that is to have enough statistical significance to detect the true nulls. And then we also need to balance that with not falsely rejecting the null hypothesis when there is no treatment effect. So in what follows, we're going to focus on this studentized test statistic for difference in means, which we generally use for estimating our treatment effects. And we're going to derive the MDE based on this test statistic and associated distributions. So given independently drawn observations for treatment and control, the significance level of our estimate for a given alpha is going to be provided here below as the difference in means over the standard error, right? So this is just the difference of means in the treatment minus the difference in the, this is the mean of the treatment minus the mean of the control over the root of the variance over the number of observations, and that's going to give us our test statistic. And then similarly, the probability of committing a type 2 error is provided below. And then we can combine these two equations and solve for the MDE that yields the following relationship, which we see as a function of the t-values based on alpha and beta, the variances, and the sample size allocated to each treatment. And then this here is what's going to determine the smallest value of the average treatment effect that we'll be able to detect and correctly reject the null hypothesis. So now we can use this actually to solve for n. In the most straightforward case, if we assume that the outcomes will have the similar outcome variance and that the treatment and the control have the same number of units, we can actually simplify this equation quite a bit further by skipping over a couple of steps. And then the equation here that's shown, equation 7, this n star is going to give you the number of units that you're going to have in each group. So here we see n star is just equal to 2 times the sum of these t-values squared, which is about 16, times the variance over the square of the MDE. So this provides insight into the relationship between some of the components of the calculation and the minimum sample size needed for a particular MDE and the level of power. So for example, we can see that the optimal sample size, n star here, is going to increase proportionally with the variance of the outcome. So if we have higher variance, we're going to need more sample size to be able to detect our effect. And it also increases nonlinearly with the significance level and power of the test. And finally, proportionally with the square of the MDE. So we can actually use this equation quite quickly to calculate necessary sample sizes when we think about MDEs in terms of standard deviations here. Because if we have this standard deviation here over the MDE, which we can express as 0.3 MDE, for example, those cancel each other out, and then we just have 0.3. So for example, if our MDE is 1 standard deviation, which is quite large, then this would mean that we would need an n of about 16 in each treatment group, or a total n of 32. So if it's half of a standard deviation, then you can do the calculation yourself, but it would be about 63 per group, or 126 total. And you can try it yourself with different different MDEs to see how that affects the optimal sample size. And finally, if you use something like 0.1 SDE, you can see that we are going to need a total sample of about 3,000. So you can see here that like with this sort of basic design and a couple of assumptions, you can quickly calculate a rough sample size. So now we can also make an adjustment for the total N when the variances are different across the outcomes. Here we can learn a lot about the total N needed from these equations, including that this is going to be increasing in the MDE. But we also notice that the relative distribution of the units across treatment and control is actually proportional to the standard deviation of the respective outcomes, meaning that if a treatment has outcomes, we should sample more from that treatment. And you can use these equations to actually solve for what those values are. So I'll go through a quick example to illustrate this fact. So in a paper by John in 2001, he used this value elicitation framed field experiment at a sports card show to explore how agents bid in Vickrey second price auctions. So we're going to focus here on the comparisons of the two treatments among non-sports card dealers in which they're either giving hypothetical bids or actual bids. So previous work actually suggests that in general, valuations in hypothetical bids have a greater variance than the valuations in tasks that are monetarily binding. So here's a situation in which our outcome variance might actually be different across treatment and control. So while in this case there were different costs across treatments, we're going to assume constant costs for now. So given the previous evidence, should the author have had the same number of observations in the treatment and control, given the higher expected variance in the hypothetical bids? And the answer is that no, he shouldn't have. So instead, the previous work suggested that that there would be a 2-to-1 ratio of standard deviations, which would require a sample size that was actually 11% larger than what was collected with in the experiment, and that it should be based on the ratio of the standard deviations to achieve the same level of power. So using the equation that I showed before, for the sample power and total sample of 175, the optimal sample sizes would have been about 111 in the hypothetical group and 64 in the actual group, which is about 2-to-1, which is the same as the ratio of these standard deviations. And actually, the uniform design that John used in this study decreased the power of an already underpowered experiment from 69% to 66%. So now we'll talk about a situation with dichotomous treatment, so one treatment and one control, with binomial outcomes. So the formula we derived above for the continuous outcomes case in a between subject design can be adapted for other common experimental designs, including within subject designs, cluster designs, continuous treatments, and binary outcomes. And so I'm going to show you this example with binomial outcomes with binomial treatments to give you some more background on how to do this. So a binomial outcome, you can think of an outcome of a treatment such as the take-up of a program, for example, or the decision to get vaccinated, or any number of choices that your subjects might make that are binary. So similar to the above continuous case, we're going to assume that the normal approximation can be used to approximate the test statistics. And for binary and count data, unlike the continuous case, the variance will actually depend on the mean. So we really have to take that into account when we think about the equation for the minimum detectable effect. So let me move forward to show you how this equation looks. So using this normal approximation of the binomial distribution for binary data, the variance is going to be equal to P times 1 minus P, where P is the mean of the outcome variable. So if we set the null hypothesis of equal proportions under the treatment and control, so H0 means P0 equals P1, that means that there's no differences in the probability of take-up. And then using the equation 3 for the null hypothesis of equal means, and then similarly, for the alternative hypothesis, we're going to assume that P doesn't equal to P, so they're going to have different means and therefore different variances. What that's going to give us when we put that into the framework we had before for the type 1 and type 2 error we're gonna get the optimal n is gonna be equal to this equation here. So I'll give you a second to look at this and think about what this means. But in general, the variance here is going to be maximized for p equal to 0.5. And therefore, the optimal sample size is going to increase as p bar here, which is the sum of the probabilities over 2, approaches 0.5. So rather than just thinking about one treatment, in many cases, we might actually be interested in multiple treatments of the same at the same time. So for example, in pricing experiments at Lyft, they might vary the price for a specific route over a range of prices. This might be as many as 12 prices across 50-cent increments. Like in my own work, for example, we're currently studying match savings, for which the value of the match can take on 4 different levels. So many times we're interested in multiple treatments rather than just one, and we can think about how that's going to affect our design. So let's revisit our first equation and think about estimating treatment effects in this context and how it's going to affect our power. And this is our estimating equation here. So we originally considered the case of constant treatment effects, so that treatment and control outcomes have the same variance. And now we're going to consider a range over which the treatment variable can vary from 0 to d bar here, and think about how to maximize precision and what to consider to minimize the variance of this treatment effect. So again, we're going to be thinking about the variance of this treatment effect given by this equation here, which is the variance of the unobserved component over the sample size times the variance of the treatment effect. And so for this equation here, we can see that there's potentially a number of ways to reduce the variance of this treatment effect. One is clearly to increase the number of observations. Another is to decrease the variance in the unobserved component. But then finally, what we can do is we can actually increase the variance of the treatment. And so how do we do that? So what we can do here, and what we can see actually, is that if we triple the variation in D, this would actually have the same effect on precision as tripling the sample size. So we have a potentially cheap way of getting more power in our experiment. So let's first think about the linear case. So if we think about if the treatment effect is linear, so let's say we have a theoretical prediction about demand, or you have strong priors that the effect is linear. And by linear, what I mean is if you increase from 0 to 1, that's going to have the same increase on your outcomes as an increase from 0 to 2. The optimal way to increase the variance is going to be to increase or to put half of the sample at d equals 0 and the other half of the sample at d bar, or the maximum possible value. So doing so is going to maximize the variance and minimize the standard error of the treatment effect. So let's say you have a potential number of outcomes. So instead of putting that treatment effect, instead of mixing it up 0, 1, 2, 3, 4, the best way to increase your power is to put half of your sample at 0 and the other sample at 4, because you're making the assumption of linearity here. So then this is going to get us back to the power calculations we considered earlier for the continuous outcomes with binary treatment. And then we can revert to our sample size determination using the standard deviation and minimum detectable effect size. If, however, our theory predicts a nonlinear response to treatment, then we need to make some adjustments to maximize power, and because we can no longer put half at the extreme and half in the control. So instead, identification is going to require that the number of cells that we use should be equal to the higher polynomial order plus 1. So if we want to test a quadratic effect, we're going to have to need 3 treatment cells. And if we want to test a cubic effect, for example, we're going to need 4, et cetera, et cetera. So for the quadratic case, if we want to test this quadratic effect, the treatment cells should be chosen in the feasible range, and they should be at the extremes 0 and d bar, as well as at the midpoint. So this tells us where to put the treatment values, right? So we have 1 at 0, 1 at the maximum point, and then 1 at the midpoint. But then the question is, how do we set the number of observations in each cell? So intuitively, the test for the quadratic effect will compare the mean of the outcomes at the extremes to the mean of the outcome at the midpoint. And as before, the variance is going to be maximized when equal proportions are allocated to these two means. And so the midpoints and the midpoint and then the extremes. So how do we do that? So we can equally divide the extremes so that the optimal proportion in each cell would then be a quarter. And then the other half of the sample would be at the midpoint. And then similarly with higher order polynomials, the problem becomes more complicated, and I'll leave it to you to look in the book when it comes out for further guidance on this. And then just to follow up on that quickly, many times we might have different levels of treatment, but rather than being continuous, so 0, 1, 2, 3, they might be ordinal or unordered. There's less guidance in this context, but the key is to determine which contrasts are of primary interest. So let's say that there's 3 treatment scenarios, A, B, and C, and you are interested in comparing outcomes in the baseline scenario A with outcomes in our alternative scenarios B and C, but you're not so interested in comparing B and C with each other. In this case, the optimal allocation should be more weighted towards A, since A is used in 2 contrasts and B and C are just used in 1. So you can think here, our treatment allocation might be half of the sample in A, and then a quarter in B and a quarter in C. So when you're using those sorts of outcomes, you need to think about the proper comparisons to figure out how to allocate your treatment to the different, or to allocate your sample to the different treatments. So now we'll talk about cases in which the costs of treatment and control might be different from each other. This can occur when your treatment provides a good or a service that's costly. You might be dealing with a very expensive, for example, anti-poverty program with components that all have different costs, or you might be paying workers different wages, and the expected cost is different across treatment conditions, conditional on effort. And when we take into account varying costs of treatment, our optimal sample size becomes significantly more complicated. So now, instead of just thinking about allocation of units to treatment and control, we need to take into account the per unit cost of applying the control and treatment, and include that total cost as the sum of the individual costs times the corresponding number of units in each treatment cell, and that's going to be given by M here. And so what we're going to do is we're going to try to think, we're going to go back to the MDE equation, and we're going to include this as a constraint, and then try to find the maximum values here to solve for how to set our and how to allocate our treatment and control under these cost conditions. So we go back with these different MDE with the potentially different sample sizes and try to solve for the allocation to treatment that maximizes the MDE subject to the cost constraint. Solving for N0 and N1, the optimal sample sizes are given here by this equation. So this ratio of N1 star over N0 is given by pi 1 over pi 0. And what we see is that the optimal sample sizes are going to be proportional to the standard deviations of the respective outcomes, which we saw before, and then inversely proportional to the square root of the relative sampling costs. So this implies that if the sampling costs for the control group are smaller than for the treatment group, then the control group should be larger than the treatment group. And since the optimal sample sizes are proportional to the square root of the cost of sampling, this really becomes important when there's when the differences in costs grows large. So let's assume that the standard deviations are equal to each other. Then, for example, if the sampling costs of the treatment are 4 times larger than the control, then the rule is simple. We just need half of the number of units in treatment than in control. And then knowing this, you can then calculate the total sample needed for your desired minimum detectable effect size subject to your budget. And you can try, you can go ahead and try these with other cost assumptions and play around with these ratios to try to figure out what would be the optimal allocations to treatment and control. So I just explained this, I'll move forward. So here's a quick example of how this might go wrong, or how different costs might arise in an experiment. So in a 2000 paper, Dean Carlin and John List partnered with a charity to help raise money using a field experiment. So we're going to think about this problem with a significance level of 5%, power of 80%, and then a fixed budget. So in their study, they were trying to estimate some key parameters in the theory of charitable fundraising, focusing on the demand side. And to do so, they solicited contributions from more than 50,000 supporters of an organization, and then randomized households into groups based on the amount of money that donors would match. So they wanted to test whether larger match ratios induced more charitable giving, and they used 3 treatment cells corresponding to match ratios of 1:1, 2:1, and 3:1. And what that means is that in the case of 1:1, if somebody gave $100, the charity would actually receive $100 from an anonymous donor, and together that would result in $200 for the charity. So here, there's obviously large differences in cost across treatment, right? So you could think in a 3:1 match, that cost grows considerably. So suppose that theory suggested a linear relationship between giving and price. What should Carlin and List have done under the assumptions that we made earlier? So if we were merely interested in estimating a linear price over this range, as we showed earlier, they would want to put half in the 1:1 and a half in the 3:1. But due to cost concerns with equal allocation across treatments, the MDE in their design is about 22% higher than that of the 2-treatment design. So because they had higher costs, they had to allocate part of their sample to this 2:1 treatment, and that actually increased their MDE significantly. Or put another way, the 3 treatment cell design requires about 50% more observations than the 2-treatment design. So if they wanted to test a quadratic effect instead of a linear effect, and which we learned previously would mean that half of the sample would be in the 2:1 match, with the other half allocated evenly across 1:1 and 3:1, this would result in an MDE that's about 41% higher than the 2-cell treatment design for linear effects in the case of no differences across in costs. In practice, however, as I said before, they had to consider the costs of sampling, but the example illustrates the trade-offs in power with different designs and how taking costs into account can potentially change dramatically your power calculations. Okay, so I see a quick question in the Q&A. Isn't assuming linearity very restrictive? So that all depends on your experimental design. So if you're thinking about, if you have some sort of priors, you're testing a theory that's linear, like I said, let's think about potentially a linear demand curve, then that might make sense. In the case of match ratios, I think linearity probably would be pretty restrictive, but that's something that the researcher would have to take into account when they're thinking about their theory or the test that they're trying to perform. But you can see how, even from this question, isn't linearity very restrictive? Yes, it potentially is very restrictive, and that's going to change the way in which you allocate your sample to treatment and your total sample size. So that should be kept in mind when you're coming up with your research design. So thus far, we've maintained assumptions that have been that the unobserved components are independently distributed among units. However, there's a possibility of correlation in the observed components among units, or in the unobserved components among units within a cluster, and that can be a nuisance when coming up with your power calculations. So clustering is going to play a role in every experiment type, from sessions and laboratory experiments to, say, villages in the frame field experiments in developing countries. Some experiments feature cluster randomization, in which clusters of individuals rather than independent individuals are randomly allocated to intervention groups. So under these cluster randomization trials, the outcome of interest, we might observe it at the individual level. So let's say this is the incomes of individual farmers, but the randomization occurs at the cluster group level. So the randomization might occur at like the village level, for example. So this implies that the unit of randomization is actually different from the unit of statistical analysis. And this lack of independence among individuals in the same lab sessions or in the same village affects both the optimal sample sizes and the analysis of our experimental results. So assuming equal variances, the optimal sample sizes, let's see here. Well, I'll go back to this just to give you an idea of what the sort of estimating equation looks like, since you can see here Yij is going to be the outcome variables, and we have Y, which indexes the individuals, and J, which indexes the treatment clusters. And we see when we estimate this average treatment effect, the D is going to be given by the cluster level. And in this scenario, if we're sampling by cluster, each cluster is of size M. So that would be, say, 10 units per cluster for both treatment and control groups. And we can allocate, or we can derive the optimal number of units to treatment and control using our previous derivation. And now it's quite similar to what we had before, but it's going to be scaled by this variance inflation factor here, which is 1 plus the number of units in each cluster minus 1 times rho here. So rho is what's called the intercluster correlation. And that's given by this equation here. So this coefficient of intercluster correlation, if it's very low, and this ranges between 0 and 1, if it's very low, what that basically means is that there's not a lot of correlation in outcomes or the unobserved component within clusters. And if it's very high, what that means is that the correlation in that unobserved component within clusters is very high, meaning that you don't get much information from each unit in a cluster. Most of your variation is going to be coming across clusters rather than within clusters, which would mean that you would have to sample more clusters. You can increase M as much as you want, but each M is not giving you much information. Rather, most of your information is going to be coming from variation across clusters. And what we see from this equation is that the total sample size needed in a cluster design is going to increase proportionally with both the size of each cluster and with the intercluster correlation. Another thing to consider also in, okay, so Alexander in the chat asked how to find out rho. So rho can be calculated generally when you're doing your power calculations. One way to do it is to use rhos from similar studies. What I've done in the past is you look at your main outcome variables. So let's say you specify 6 outcome variables that you're interested in. There's a way to calculate the intercluster correlation in whatever statistical package you're using of those outcome variables. So you can go to Stata or R, whichever you're using, and there's some commands to calculate that rho for you, and then you can use those in your power calculations. And what I do generally is I come up with bounds for those rhos, and then I simulate different power or estimate different power under rhos and try to come up with the rho that gives me the most power conditional on the size of the experiment. So many times you run up against cost constraints, and you're going to try to choose the rho that's the most conservative for you to be able to have sufficient power to detect your effects. Okay, let's see another example. As per your early example for 3 groups A, B, and C, if you want to compare the MDE between each of the groups with 2 other groups with the optimism. So Marna asked this question about comparing A, B, and C. If you want to compare the MDE between each of the groups with the 2 other groups, would the optimal design be to assign equal numbers of the participants? So you're going to get, so if you're going to compare A and B, B and C, and A and C, then yeah, the optimal allocation is going to be 1, 1, 1, or 1/3, 1/3, 1/3. That's going to minimize your minimum detectable effect. Thanks for that question. So a couple other things to consider when you're thinking about cluster designs is that your degrees of freedom, where K is the number of clusters, is going to be smaller in the cluster design, and this is going to reduce your power a little bit. So you need to take that into account. And in the presence of intercluster correlation, it's important, if possible, to randomize over as small clusters as possible to maximize the efficiency of the experiment. That it's kind of what I said before. So if you have very high intercluster correlation, you're going to want to randomize over small clusters. So clusters of 1, 2, 3, 4 people, and then you're going to have mini clusters. So one thing to consider again in a cluster design is cost, in which we think about both the per unit cost as well as a fixed cost per cluster. So we got another question. What would be an acceptable K number of clusters? So here, so under the no cost situation, what this is going to do, so this is going to solve for the optimal number of your sample size in each treatment condition. You'll have the M here, and so you can use N times M, and that's going to give you the optimal number of clusters, right? So depending on, you would choose your M based on your row to solve for the optimal number of units, total units, and then multiplying those together would give you the optimal number of clusters. And the acceptable number of clusters, again, what acceptable meaning sufficiently powered is all going to depend on your intercluster correlation. So going back, we can consider costs as well. If we have a per unit cost as well as a fixed cost per cluster, what we can do is we can maximize that minimal detectable effect size subject to this constraint, and the MDE for this subject to the budget constraint is going to lead to this expression below. So what we can see here is that the optimal cluster size, that is the number of units in each cluster, is going to be proportional to the square root of the ratio of the fixed cost per cluster and the cost per unit, and then also to the ratio of the standard deviation of the within and between cluster variation. So the optimal cluster size is going to be independent of the total budget available for the experiment. This indicates that on a limited budget, the experimenters should first work out how many units to sample from each cluster, and then sample as many clusters as possible. And as I said before, from Yvonne's question, the optimal number of clusters K star can be found by substituting this M back into the equation I showed before here. So you can put that in here, that M star, and then solve for the number of clusters, keeping in mind that N equals M times K. So the total number of units equals the unit per cluster times the number of clusters, which I show here. So another problem that arises in experiments is the possibility that compliance might not be perfect. And this should be taken into account when you're determining your optimal sample size. So this is actually quite a big problem. When you're not doing natural field experiments, when there's in other types of experiments in which you even in natural ones where people are selecting into treatment, you really have to take into account compliance when you're determining your optimal sample size. So if this is the case in your experiment, what we see here again, we revert back to our optimal N equation, but we're going to add on a different component here. And what this is the ratio of the difference between the initial treatment and the control groups to the difference in the probability of being treated in the treatment groups is an estimate of the causal effect of the treatment among compliers. So here C is going to be the share of treatment group that received treatment, and S is the share of the control group that received treatment here. So what we have is, so if let's say in the treatment group we have compliance of 0.8, and in the control group we have compliance of 0.9, that's going to be this value here in the denominator is going to be 0.1. We divide by that and then square it. That means we're going to have to increase our sample size by, that's going to be N times 100. So you can see quickly that imperfect compliance is going to play a big role in your sample size calculations. And so, this partial compliance is strongly going to affect the power of your design, since your MDE is going to be increasing linearly with that compliance rate, and then proportionally with the square root of the number of observations. Thus, if there's an 80% difference in the take-up rate between the treatment and the control group, the sample size would have to be about 56% larger to achieve the same minimal detectable effect. Alternatively, at the same sample size, the minimal detectable effect would be about 25% larger. And I think that this underscores the importance of compliance in experiments, And if you have the choice between two different designs with different levels of compliance, you might want to choose the one that will have the highest compliance, which can have important implications on your sample size. So suppose, for example, you want to evaluate a voluntary business training program for some microcredit clients. First approach would be potentially to use an encouragement design, where you randomly select clients to be asked whether they want to participate in the program, and they could choose whether to do so or not. And then the evaluation would then compare those invited to those who were not invited, and you would use a sort of instrumental variables designed to estimate this local average treatment effect. A second approach would be an oversubscription design. So that would be the case where clients would be asked to apply. And in the program, so let's say you have 1,000 people that applied, but you can only give it out to 500 people, then you would randomly allocate these applicants to the treatment or control. So the take-up of the program in the second design would presumably be much larger than in the first design. And then the MDE for the effect of the training on those who choose to participate when offered the option would then decrease in proportion. You can estimate, you can have a much smaller sample size if you do it this way. So some things that I wasn't able to cover here, given the limited time, but that's left in the chapter, and things that you should consider when you're designing your experiment. One is panel data settings. So in many cases, if you have more time periods, that's actually better. So there's a great paper by David McKenzie in 2012 on the importance of using baseline data. But then given the level of serial correlation in outcomes, many time periods can actually be worse. So there's a great discussion of some recent papers on what to consider in panel data settings in the chapter. In addition, many real-life situations are going to depart from these standard assumptions, and we might want to use simulation methods to try to come up with our optimal sample size and minimum detectable effect. Another one is multiple hypothesis testing. So as we're testing, if we have many different hypotheses that we're testing, when we consider them jointly, the test needs to be changed significantly to consider the likelihood of a false positive on any of these tests. So those need to be taken into account. And there's a number of resources thinking about multiple hypothesis testing, so you should go out and look at those whenever you're designing an experiment that has multiple hypotheses. Now you have to adjust for multiple hypothesis testing, so please go out and seek that out, or wait for the chapter when it comes out. And then there's a number of other design and analysis considerations for increasing statistical power that are covered. So that's covariate adjustment. If you include more covariates in your estimates, you can reduce the variance of that of the unobserved component, and that's going to improve your power. There's also sample selection. So the way that you select your sample might matter. You might want to select to reduce the variance in outcomes. You might want to select observations that are more similar to each other rather than those that are very different. And then there's different measurement choices you can take. So this comes into measurement bias and systemic bias that comes from your measurement. So you need to take into account some of these measurement choices when designing your study and thinking about power. And then just to give you some quick tips for power calculations with your partners when you're thinking about coming up with a study design. One is to start from the very beginning. As I said at the start of this talk, you should always be thinking about power at the very beginning. And then you'll know sooner rather than later if the study is possible. If you don't think about this and you think about it towards the end, you'll find out that basically everything that you've done might have been useless because you won't actually be able to detect an effect. If you don't have data, try to use existing data from public sources and then refine over time. So it's very important to pilot. So if you can do pilots, that'll help with your compliance rates, for example, and then you can reallocate or rethink about how to design your experiment. Maybe you can reduce treatments or increase treatments depending on what your power is from that piloting. And then it's always important to discuss with partners, and I run in this all the time, why sample size is so important and to come up with a common understanding. So they might not understand some of these different trade-offs, and if they really want to detect an effect, it has to be sufficiently powered, because even if you do detect something and you don't have enough power to say whether it's true or not, then the value of your experiment goes down significantly. Again, it's not an exact science. If you're in doubt, gather more data. And always remember that take-up, compliance, and attrition can have a large effect on power. So with that, I'll wrap up and let Julia get started. Thanks, everybody, for coming. Julia, I don't know if we have time to answer any of these.
Yeah, you have 2 more questions. If you want to take them, like, it's
okay,
totally fine for me.
Yeah, I find it tricky to estimate the MDE. Yeah, I think everybody does. I mean, it's always hard to come up with an MDE. Many times that will come from partners themselves. So if you're thinking about, they're thinking about scaling up a program, or, they'll have many times ideas of what the MDE should be. Like we only want to do the study if we can detect an effect size of this size, and that this will justify the cost of the program or scaling up. Otherwise, like I said, you can look at other studies, or it can come from your theory. So just make sure that it's enough to detect what you need to either justify the program or to test your theory. Okay, so Zara asked a question about heterogeneity of the individuals of the treatment effect. So yeah, I didn't talk about stratification here. So here's going to be a situation where you're going to need to think about stratification. So you want enough of your sample in the different types of heterogeneity, so that you can sort of try to estimate the heterogeneity and the effect across different types of individuals. So that's another consideration that I didn't include on the slides either, is stratification, and that's going to affect your sample size calculations as well. And then I'll just answer one more. And then the rest of them I can take in the chat. If an underpowered study finds a significant result, can one argue that we cannot trust the result, or can we assume that the effect is so big that even an underpowered study found it? Oh, no. So yeah, I mean, here, if you find a significant result in an underpowered study, so you have to think about here is a situation with your with your significance level, but you can generally assume that the effect is going to be so big that even an underpowered study found it. So if you do find an effect with an underpowered study, that would generally suggest that you actually had that the treatment effect is just large enough. So if you had you were able to detect an MDE of 0.5, but you actually found one of 0.1, that's not a bad thing. That just means that the effect size is larger than you anticipated, and you're able to detect that statistical significance. And Alexander says it could be a false positive. That's correct. It could be a false positive, but you need to make sure that with the significance level, yeah. So you would need to go back and make sure that that's a false positive. But if you have a significance level of 0.95, it's only going to be a false positive 5% of the time. So that's a problem that you run into with any study with the significance level. So with that, I will stop sharing my screen.